Hello friends, today we are discussing work, power and work energy theorem. Before going to start, we know the conservation laws. A number of conservation laws are known to us. Most of familiar examples are the laws of conservation of energy, laws of conservation of linear momentum, laws of conservation of angular momentum, and laws of conservation of charge, etc. These laws are usually the consequence of some underlying symmetry in the universe. Conservation laws are very powerful tools for solving the problems in physics. A few of advantages like conservation laws do not depend on the details of the trajectory of a particle. Since these laws enables us to state very useful and general consequence of equation of motion. These laws have been used in the physics of elementary particles. We know the elementary particles, protons, neutrons, electrons, mesons, neutrinos, etc. are known as the elementary particles. Conservation laws are the most striking physical facts which have been used in tackling of new and not understood problems. Sometimes conservation laws predict the certainty that particular phenomena will not occur. A conservation law may be used conveniently in solving the problems for the motion of particle. Even if we know the force involved exactly. For solving a problem, first we use the conservation laws, and if there remains anything to the problem, we make use of other methods of the calculation. So as we know the laws of conservation of energy, that is the energy cannot be created, cannot be destroyed. Like the linear momentum, the rate of change of momentum of a body is proportional to the force acting on it. For angular momentum, the angular momentum of a particle about a fixed point is defined as the moment of its linear momentum about that point. So these are the examples of conservation of laws. So today we are discussing the first, that is the work. What action takes place when the football player kick the balls? The net force is applied on the ball so that ball is moving from one player to other player. The first player kicking with the initial velocity and then final velocity. So there is change in energy of the object. So work takes place when the person hitting the kicks, the works takes place. What is the work? वर्क क्या होता है? मेजरमेंट ऑफ एनर्जी. अब ये इक्वल होता है, जितना हम फोर्स अप्लाई करेंगे उतना ही वर्क नेट फोर्स के इक्वल होता है. सो व्हेन फोर्स एक्टिंग अपॉन एन ऑब्जेक्ट टू कॉज अ डिस्प्लेसमेंट of the object, whatever it may be, in various forms. Suppose we are pressing the spring is going to decrease the shape. When you are releasing the force, the spring is going to its original condition or the increase in an object. Here, when the increase and decrease of energy of an object. When the press release it, the energy is increased, or we can say the spring is increased, and when you are pressing it, decrease in the size of spring. So as we know, the work is the measure of energy. So first, observe this. A stable object is here and the person pulling the object with the net force. So for every moment, the angle will change, and that force, that net work done is equal to force into their displacement, that is the F into dr. With the help of this image, here we are trying the path of an object. So let us consider particle P, this particle P moving along a curve AB under the action of variable force, capital F. Here force will be different, here force will be different, here force will be different. So the force is variable. Let at any instant, here I am taking this arrow, dark arrow, the position vector of the particle be R from P to this point. If this force F displaces the particle through a distance dr, then the infinitesimal small amount of work, that is the dW, done by the force. So here another dW is here, then another dW is there. So from A to B we get the total work done. So this work done by this force on the particle is defined as dW into F dr, like this one. But here the angle will change, so tangential force will be changed. So if the force makes an angle theta with the tangent to the path at any point, then we can write the work done W is equal to integration of A to B into F dot dr. So first dW is equal to F dr. Then the path is there, A to B. If the particle is moved from A to move from a point A when position vector is R1 to the point B whose position vector is R2, then the total work done W is equal to integration R1 to R2 F dot dr. Then force makes an angle with a theta, makes an angle theta with a tangent to the path. So we can write the W is equal to A to B F cos theta dr. So here the values of F and theta may change from point to point of the path of the particle. In general, for any other vector which is a function of an integral of the form. So integration of A to B dot F dr is equal to integration of A to B F cos theta dr along some line, that is the AB, is called the line integral. Since F cos theta is the component of force along the path, so the work may be defined as the line integral of tangential component of the force taken over the actual line of motion, or we can say that when a force acts upon an object to cause the displacement of the object. Sometimes it is convenient to represent the tangential component of the force F cos theta is equal to Ft. So dW is equal to Ft into dr, and Ft is the function of distance r. So here this is the function of distance r graphically. The amount of work done, dW is equal to Ft dot dr. So amount of work done during a small displacement dr corresponds to an area of the narrow rectangle. This is the narrow rectangle here by a shaded region, we can say shaded region. Then the total amount of work done, that is the W, on the particle here, W is equal to A to B F dot dr is equal to F dot r is equal to F dot cos theta r. This expression for the amount of work done is in accordance with the elementary definition of work. That is, the work is the product of the component of force along the displacement and the distance moved by the particle. So here the force along the displacement and distance moved by the particle with r. Now work is the product of the component of force along the displacement and the distance moved by the particle. If we are taking the Fx, Fy and Fz are the rectangular components of the force F, so dr is equal to dxi plus dyj plus dzk. Then the first equation becomes the work done is equal to integration of a to b fxi plus, this is the value of f, that is the fxi plus fyj plus fzk. So here not the minus sign, it is the subscription symbol, so by mistake I am writing the fzk dot dxi plus dyj plus dzk, so that the resultant force on the particle is F is equal to integration of a to b F dot dr is equal to integration of a to b all the forces F1 plus F2 plus F3 with their corresponding components and into dr. So we can write the work done is equal to integration of a to b for first force, that is F1 into dr, then integration of a to b F2 into dr, and so on. So this is the sum of work done by each force. Now the question arises, here the work is done and that work is with the rate of doing work is defined as a power. So we can simply write P is equal to dW by dt. So if F is the instantaneous force acting on the particle, then we can write P is equal to dW by dt. The term is equal to the force acting on the particle, that is F into dr by dt. So we know the W is the nothing but dr, F dot dr. So dr by dt is nothing but the velocity. So we can write the power is equal to the force into velocity. which is the expression for the instantaneous power. The average power during a time interval t is obtained by dividing the total work by time. So the average power is equal to capital W by T. Now we can relate this work done. Some work is done on the object or by the object, so energy changes, and that is the kinetic energy. So now we can prove that the kinetic energy or work energy theorem. The energy of a particle is defined as the capacity of doing work. क्या होता है कि हम एनर्जी का डेफिनेशन किसको बोलते हैं कि जो एनर्जी वर्क के काम में आती है, वर्क करने के काम में आती है, दैट इज द रेट ऑफ डूइंग वर्क or the capacity of doing work is the energy of that particle, and it is measured by the amount of work which it can do in the position in which it is. अब एनर्जी कैसे होती है? वो एनर्जी होती है स्पीड ऑफ पार्टिकल के हिसाब से. मतलब इफ द एनर्जी इज एट रेस्ट, द पार्टिकल इज एट रेस्ट, that is the potential energy. But if the inner particle is in motion with their speed, so the energy due to the speed of particle is called kinetic energy. Kinetic energy हम किसको बोलते हैं? जो मोशन में होती है, जिस पार्टिकल की स्पीड अच्छी होती है या कुछ मोशन होता है, उस पार्टिकल के एनर्जी को हम क्या बोलते हैं? काइनेटिक एनर्जी. एंड इट इज जनरली रिप्रेजेंटेड बाय कैपिटल के. As we know the second law of motion, that is related to the force according to Newton's second law of motion. So F is equal to m into A. But A is what? Acceleration. Acceleration is nothing but dv by dt. That acceleration produced in a particle of mass m by the force F. So the amount of work done on a particle when it is taken from the point A to the point B is given by W is equal to A to integration B F dot dr. So substitute this value of F. So we get W is equal to m into integration of A to B dV by dt into dr. As we know, the dr is nothing but dr by dt into dt, just for the simplification. But dr by dt is nothing but the velocity, so we can substitute this value, so we get v dt. So dv by dt dot dr, this value with the dt is equal to dv by dt into v into dt. Just rearrange it. So d by dt into 1 by 2 v dot v dt minus d into v square by 2. Since w is equal to m by 2 integration a to b d v square. Here v square is the initial velocity and final velocity. That's why we're taking it. So we can write w is equal to m by 2 v square in bracket a raised to a to b. So we can write w is equal to m by 2 in bracket vb square minus va square. Here va and vb are the speeds of the particles at the point a and b respectively. So thus we can write w is equal to integration a to b f dot dr is equal to half mvb square minus half mv a square. So we are subtracting the final velocity and with minus velocity, initial velocity. This equation shows that The work done on a free particle depends upon initial and final speeds of the particle and is independent of the nature of this force and the path followed by the particle. As we know, half mv square is called the kinetic energy of the particle. In case of if a particle has an initial speed v and finally it acquires zero speeds against a force, then the work done by the particle against the force is W is equal to minus f integration of f dot dr. Substitute the value and we get the minus m by 2 integration initial value to 0 dv square. So we get half mv square. Thus a particle of a speed v has the capacity to do half mv square work. This means that half mv square is the kinetic energy of the particle. So we can say that the work done is equal to kinetic energy, but kinetic energy at B, that is the kb, minus, this is the final value of speed, minus kinetic energy of, सॉरी यहाँ पे मुझे भी a लिखना चाहिए था. So kinetic energy at A. So this differentiation is nothing but change in kinetic energy. This is known as a work energy theorem, and this equation is represented by in form of equation 2, that is kinetic work energy theorem. So go to the your first. So this second equation, W is equal to half mv b square minus half mv square mv a square. This equation representing the work energy theorem. So this is the work energy theorem. So thank you for watching this video. In next session we are discussing the more interesting concept. So have a nice day. Thank you very much.